After understanding the signal here, right, which is basically we are talking about radioactivity that is of interest, and in the radioactivity we talked about different modes of decay, and two of which will be exploited, namely both of we are interested essentially in the gamma energy that is coming out, right. So there is this transition, isomeric transition, which gives out gamma, and then you have this annihilation of positrons which again give out gamma. So we are interested in radioactivity, and the radioactivity giving out gamma rays, right, the source is inside the body. So now the objective is how do we capture this on the outside and tell where the source is, where the radioactivity is. That is the big difference between the X-ray photons interaction with the tissue that we studied earlier and exploited in projection radiography and CT, where attenuation was the material property of interest. Here we are not actually interested in the material property of the body. We are giving radioactivity and we want to locate where the radioactivity is coming from the body. Okay. So what we will do now is we will try to in some sense draw a parallel between how we did for X-ray after we completed the physics of X-ray, right. How is X-ray generated, how is it interacting with the tissue of interest. Then we quickly talked about different modalities. One was simple projection radiography, the other was after you collect the data from different right projections in different views, how do we back project and get the slice, tomography. Similarly here, when we come out, when the gamma rays comes out from the source, right, emitted from inside the body, right, we have to collect it. So there are three different imaging modalities of interest here, okay, which exploits the gamma rays, which essentially count the radioactivity. First is drawing parallels, we have projection radiography. Similarly, we have what we call as planar scintigraphy. Here very straightforward, you put the radio tracer in and this starts to give out gamma radiations, right. So gamma photons, of course it will come out and it will give out throughout the body in all the directions. So if you keep a detector on one side, right, in one location, what is going to happen? These photons can be captured in that direction, and in some sense it is very similar to your X-ray projection radiography, where you had a detector, right, a detector, rectangular shaped detector behind the body. So the whole area was captured, the projection was captured. Here you are going to have a detector that is going to detect where the gamma rays is coming from. So our interest is to, from the image, tell how much of activity came and from where it is coming. Okay, so these are the two things. For this we will use what is called as Younger scintillation camera. In fact, this has been there from the beginning of using this nuclear medicine aspect. So this camera is an important part of enabling the planar scintigraphy. So then what do we have? Okay, planar scintigraphy is analogous to your projection radiography. So therefore we could think about, okay, what if I take, right, the detector from different views? I could do reconstruction, right, I could do tomography. So when you do that, right, single photon emission computed tomography. Why is this name single photon? Oh, because this gamma ray photon is coming and you are detecting it on one side, okay, whichever angle you are keeping it, it is coming and falling on the detector. Single photon is counted and you get the image, very similar to your planar scintigraphy. However, you collect this data from different views and back project it. Okay. So here the same concept, it is just that the Younger uses a rotating Younger camera, right, so that you can get it from different views. So it is single photon, just to make it slightly different from what is the third one of the other modes of decay that we were interested, positron. What happens in positron? Oh, when the positron is generated, it quickly bombards annihilates with an electron and gives out two 511 kilo electron volt electron. But which direction does it give? Oh, it gives 180 degrees, right? So there you have two photons each travelling in opposite direction. So here you are just catching one photon, so it is single photon emission computed tomography. The third is positron emission tomography. In the positron emission, you are not capturing the positron. The positron gives rise to two photons, right, 511 kilo electron volt, that is 180 degrees. So you are catching two photons, right. So it is two photon emission tomography, but that does not sound well, and so you call it as positron emission tomography, because you capture these two photons and then say where probably the positron decay happened, your source. Okay. So this is your positron emission tomography, very similar to the tomography part, right. Now you understand. So you collect this data, right, it is going in 180 degrees and random directions. So if you are able to collect it from different views, then we could do the back projection and source localization. So only additional detail here is it uses a coincident detection circuit. We kind of saw this circuit, saw the diagram when we talked about the positron. We will talk about it again when we get into positron emission tomography. But the logic is very similar, right. You get the views from different orientations and then do a back projection. Okay. So let us start with the first one. So we covered the physics. So now we will talk about the instrumentation for planar scintigraphy. So here is the big picture view of what is happening in planar scintigraphy. Quickly, as we recognized this earlier, the source is inside, right. You have a radioactive tracer, you give enough time. After that, what happens? After the patient is prepared, right, you give the radio tracer, he starts to emit gamma rays, right. So we talked about the desirable properties of your radio tracer. So it is going to give, so you have enough radioactivity starting to come. So when the gamma rays, it can go any direction. So typically what happens is you have a detector, and the detector is going to catch the different gamma rays. Again the same idea, line of sight. So you want it to have a collimator so that you can eventually say where it is coming from. After you have a collimator, we will have gamma rays directly cannot be captured, right, or you do not want that. What do you want? You want some light signal. So the gamma rays gets interacted with this scintillation crystal, which converts your gamma energy to visible light photons. After you have visible light photons, it is a weak signal. So we want to amplify it. So we have what is called as photomultiplier tube, and based on the photomultiplier tube, whatever values you are getting, you digitize and do computer. So why we put computer here is this same planar scintigraphy, if you do it from different views, this data can be used for back projection. Okay. So very big picture scheme. So what we will do is we will go one step at a time, each of these, right, some of which we kind of know, we could draw parallels or analog with our X-ray part. Okay. X-ray projection radiography or X-ray CT, you can start to, if you understood that logic there, how we went ahead, it is very similar. Wherever there is a small difference in the detail because of what we want to do here. Here we are counting the energy, it is energy sensitive, whereas in X-ray, right, we were more interested in just the number of photons. So imaging principle, you capture the emitted gamma photons in a particular direction. After you capture that, you want to say where that radioactivity is coming from within the body. What is the distribution of radioactivity in the body? Okay. So again, first principle, just to reiterate, even though we will draw similarities, don't forget that in X-ray we were trying to go after this attenuation coefficient mu hat. We wanted to, right, get an estimate of how the mu is distributed. Mu hat of x comma y was your reconstructed image, whereas here we are talking about how much activity comes from where it is coming over time. That is the key. Okay. And we had lot of engineering of the radio tracers, so that we will be able to kind of tune or engineer our detection side, so that we can say where it is coming from, right. So, first part is called major part is camera, Anger scintillation camera, that is your most important part. So, this will have, right, the whole block is very important. We will try to go, because this is the key. Okay. So, what is happening here, big picture? So, you have this patient, right, the patient is sending out gamma in different directions, but in one of the directions you have this camera. In that direction you will start with collimator. Okay. So, the collimator gets in scintillation crystal, you have your conversion from gamma rays to light photons, then the light photons have to be converted to electrical quantity and it starts to multiply. So, you have your photo multiplier tubes, and then out from the photo multiplier tube you have to say position x and y, where is it coming from in x and y, right, and what is the z, is your amount of energy that is coming, okay, for that scintillation. And then you have additional circuits which can, as named here, pulse height analyzer, and then gating circuit, which energy you want to select, and then this is fed into computer, and then we will talk about what we can do, visualization or do this and reconstruct. So, the important aspect is here. So, you have the compare the detected signal to a threshold. So, here whatever comes, right, not all of them you may want to use it. So, you have this height analyzer. So, the idea is you have this detected signal to a threshold, whether we want to use that or not, because we have engineered the radio tracer. So, we are kind of looking at a gamma energy that we know that we have engineered that radio tracer, right. We showed the example of your technetium 98, you get only one energy. So, the idea is from the detected energy you need to know whether that is a one that is because of the radio tracer that is coming through the interaction, or see you have this scintillation crystal. So, maybe that is giving, so photon is interacting with the crystal, right, the thick. So, you could get Compton scattering there and you could get less energy that is coming out, Compton scattered. So, now the question is, do you want to interpret that as a signal or is it Compton scattered? So, we can be energy sensitive. If we are energy sensitive, we can say, oh, because I know what is the gamma I am the radio tracer is sending out. If it is within certain tolerance, I know it is the real signal coming from that source. If it is less than that, I know it is photon. So, you have some thresholding criteria, we will look at it. The idea here is you convert the light signal, which is, so in your X-ray, if you wanted to think about, we had this intensifying screens. So, the light photons were directly captured on the X-ray film, whereas here what happens, it is not directly, it is that light photon is further converted to electrons and then, right, compute the location. So, based on this signal you have to say where is it coming from, where is the highest activity. So, this is the rough logic what this anger scintillation camera, the whole unit is supposed to do, right. We will go one step at a time. First is your collimators. Collimators, very similar, in fact you know this. What is this? Oh, these are lead strips. Okay. So, you have different configurations. What is your objective here? The gamma photons are coming, you want only the gamma photons that are coming through, right, through the body in straight line, that is the signal of interest. So, you want to allow for only that line of sight, very similar to what we did for X-ray. So, the different configurations that are possible. So, now you have, instead of 1D, right, or what is shown here is 1D, but this is an area, right. So, it is in some sense you are looking at the plan of it, right. So, you have gaps, okay. So, which is called as a parallel hole. So, anything gamma rays that are coming through this line, it will come in, rest of it will get blocked. Remember this B by H, the grid ratio and all those things, very similar. There are 2-3 configurations that are possible. This is parallel. What if you want to say for example have a small region, right, but I want it to be blown up, zoomed in. I want that region to be zoomed in. So you could have, right, magnifies, you could have, right, B converging or diverging. So this one diminishes. So it kind of puts that big field of view into a small. So this is the difference, relationship between the field of view of the object and what is the detector area that is going to be captured. Okay, so you can, small area you can blow it into the detector's full field of view, or larger field of view you can reduce it on the detector to a smaller region. All these are possible using diverging or like so typically what they do is, it's the same thing, you flip it in one configuration, and if you want the other configuration you take it and flip it back. So and then you have this pinhole kind of configuration as well. The objective of all of them are very similar. How do I target my field of view into the detector? So we will kind of discuss more about the parallel hole, right, because we need to form the imaging equation, and then maybe for reconstruction we did pencil beam in X-ray. So if we do that here, right, with parallel hole, it might be a lot easier to make use of some of the equations that we already have developed. Okay, so collimator, nothing new on that. Scintillation detector, again here if you really think about it, it's very similar to what our intensifying screens, right, go in X-ray. What was the objective there? Convert the X-ray photons into visible photons. So here you have scintillation crystal. Even there we said in digital radiography, which we did not cover that time, we said rare earth materials have come in. So cesium iodides, those are started to, you know, becoming usage and things like that. So here is basically that part. So here scintillation crystal, what happens is for every gamma ray, right, ionization takes place and it gives out energy in the light photons. Okay. So some of the commonly used crystals are sodium iodide, right. We talked about cesium iodide, or at least I mentioned that when we did our when I mentioned about projection radiography, digital digital X-ray, or right, which we didn't cover fully. I just said we will stick with the film, but nowadays digital radiography is popular, right. So rare earth material. So I use sodium iodide, which has a coating of thallium, right, dope, and then there are few others. So that what is the, see here, what is the, you know, the big picture, what is it supposed to do? Gamma rays is coming, it has to absorb the gamma rays, right, excite, photoelectric, and then difference energy, when it comes back to the ground state reconfiguration, it sends out energy which is in the photo light right range, right. So what are the aspects that needs, or the criteria that is used for having a detector or choosing a detector crystal material? Stopping power, right. So you want the gamma rays coming, if it does not have a stopping power, then the gamma rays will go out as well, right. So stopping power, in this case the stopping power is for the gamma, it has to be a higher energy, right. Response time, similar thing that we talked about, speed of camera, right, that time. Efficiency, of course, conversion, how much photons, how much gamma photon is getting actually absorbed, conversion efficiency. And energy resolution, this is another key, because in gamma rays, we know the radio tracer is sending out a particular energy. So you want it to be having good energy resolution, so that when it comes out, we know we can stick to only those photons that are supposed to have come from the radio tracer. All the Compton scattered should not affect. So The scintillation crystal is important because on one side is the raw data that is coming from the radio tracer, on the other side is the signal estimate that you are going to work with. So you don't want it to, you want it to have good energy resolution. Otherwise, if it is going to already be lousy here, it will be very difficult to separate out which is the signal, which is Compton scattered signal. So typically you have a large area, this is supposed to be area, what is that, about 10 to 25 inch in diameter. So it's fairly, right, it's about 2 feet, little over the 2 feet, so it's a fairly big one. And look at the thickness, it can vary anywhere from quarter inch to an inch. Clearly you know the difference, why this thickness is an important parameter. Oh, you need to have stopping power. So you need this gamma rays to have time to interact and convert gamma photons to light photons. So this thickness, and what is the other issue with the thickness, that is controlled by the thickness. Oh, if it is thicker, your resolution, right, same thing affects here also. So thicker the crystal, your point spread function of this crystal, right, or this, when we talked about intensifying screens, we kind of said that. You can think about it as poor resolution or more spread out if it is thick. If it is thin, then stopping power is reduced, or right, because the material is less to interact, but then your resolution could be better. Same trade-offs are holding good here as well, but this is a little bulkier, you can see, about couple of inch thick and about 2 feet diameter. So this is going to be bulky. Okay, so now what we need to do is get into the next. So we know much about the scintillation crystal. So the gamma rays come, first is collimated, after it is collimated, the gamma photon is hitting the scintillator, right, scintillation crystal. Out of the scintillation crystal, what do you have? You get light photons, but that light photon now is, you have some number, right, depending on the conversion. But then here we need to have two things worked out. One is, I need to be able to amplify the signal, and the other thing is, this is the plane, XY plane. So what you see, this circle is, say for example, your detector crystal. So out of the crystal is going to come your light photons. In your X-ray, instead of this photomultiplier tube, right, after your crystal in the X-ray, you can imagine that you had a X-ray film that got exposed, right, photographic film that got exposed, and then we talked about the conversion, optical density, blah blah blah. Here instead of that, we have photomultiplier tube arranged like this. So that means depending on the location where the light is coming out, it will enter its, more of it will enter the nearest photomultiplier tube. The photons that are going in the side can enter the others as well, but predominantly majority will enter along the line of sight, along the collimator crystal. Out comes the crystal, it will enter the photomultiplier tube. So the objective of the photomultiplier tube is convert these light photons, right, into electrical quantity. So we'll, now what we will do is, we will see what is this photomultiplier tube. This is its configuration, it's arranged, several of them are arranged, right, on the other side of the detector. What happens? So when the light photon from the detector comes and hits the photo detector on one side, what comes on the other side? That is what we will see. So on one side you have light photons come, okay. So when it comes, it's reflected, it's going to hit your photocathode. So here what is going to happen is, this photocathode, for every 1 electron, right, for every 1 electron that is released here, I mean, it takes about 7 to 10 light photons. So in comes light photons, about 7 to 10 light photons. When it hits, you get 1 electron that is given out by the photocathode. Once this is there, you see these structures which are also called as focusing grids. These are dinodes, right? Each one is kept successively at higher voltage than the previous one. So what happens is, this is kind of used to steer the electrons. So you have, for every 7 to 10 light photons, you have 1 electron. This 1 electron now is steered, it goes near the dynode, right? So at each dynode, more electrons are released for each. So about 3 to more, as in say 3 to 4 electrons are released for each electron reaching this guy, each dynode. Likewise, you have several dynodes, okay. So you have about 10 to 14 dynodes. When you have that, what is happening? So you start with 1 electron, after the first dynode you get additional 3, 4, that 3, 4 goes into the next dynode, chain effect, so it starts to increase. So after 10 to 4, so this is why photo multiplier tube. So you see how you kind of the electrons are multiplied, right? So you go on doing this, you have successive about 10 to 14 of them. Finally you come to the anode, right? Anode is at the highest voltage, highest positively charged electron, right? So in this case, you have about, each time it is multiplied, so you eventually get about 10 power 6 to 10 power 8 electrons for each electron that was released here. So that is why it is multiplied, right, photo. So now you see the signal is actually amplified. So now this is a voltage signal. Of course, you can read this out as a voltage signal, right. So you have successfully converted the gamma rays into light photons. The light photons, it converted to your electrical signal. So you can read this out, that is your output signal, okay. So you get some millivolts to volts, right, few volts, you get that in that range. So the whole idea is, outputs are current pulse each time, this is the gamma photon hits the scintillation screen. So for each scintillation, right, gamma photon hitting the scintillator screen, you get 1 pulse of voltage. So this current pulse is then converted to voltage pulse, okay. So this is your, so one activity, so we will start from the source, from the body, one activity, right, radioactive decay. So one gamma photon comes, that gamma photon interacts with the, comes through the collimator, scintillation converts it to few light photons, the few light photons converted to 1 electron, right, and then that is multiplied through the photomultiplier tube, and you get your electrical signal out, which is supposed to be correlated to the gamma rays that came, okay. Okay, so that is your photomultiplier tube. Then what happens? After a photomultiplier tube, I have the signal, output signal. So gamma rays came, converted, I have a signal. So now what I need to do, how do I use this signal, right? First thing is, we need to, we had say several photomultiplier tube, right? You saw the configuration. Those configurations, what was shown is circular, you can arrange it in rectangular, right? So either ways you want. The idea is each one has an output. So what would be the logic? The logic is, if the gamma rays came, hit the scintillation crystal, so the maximum intensity will be on the photomultiplier tube that is closest to the scintillation, right. Rest of it is going elsewhere. So in some sense, your photomultiplier tube, you have k of them, right. Each one has an output signal that is coming. That output signal is to an input that came from a particular location in a crystal, and that particular location in crystal is directly in front of your collimator in response to the gamma rays that entered through that. So what do I want? So what is the value of this pulse height? We talked about this pulse that we are recording, okay. what is the meaning of the pulse height? Oh, pulse height is going to be related to the gamma photon energy that came, right. So, the Z pulse or the total response. So, Z pulse is nothing but x comma y. So, there are three aspects here, x, y and z. X, y is your location, right, in the xy plane. So, we will talk about that. So, you have x, y. X, y you can already think about which photomultiplier tube, right. I know where it is on the xy plane. So, roughly you can sense the location to be your xy coordinate system. What is this z? Z is your amplitude, or in this case what is the signal? Z is your activity, total activity. So, if you think about it, I have several photomultiplier tube, I had my gamma come, scintillation, converts to the light. What happens to this light? The light is spread, right, because there is a thickness. So, light spreads and it hits the photomultiplier tube, several of the photomultiplier. The closest one or the one that is straight will get the maximum intensity, rest of it will also get, because there is a spread that is happening, right. There is a interaction, there is a Compton scattering. So, maximum will be at the center or the closest straight photomultiplier tube, but the rest of them will also get something. What is this Z pulse is nothing but for each scintillation, one gamma converted, it scintillates conversion. For each scintillation, you get several of the photomultiplier tube can give output. The maximum output will be the one that is the closest, but several of them will give outputs. So, you sum all of that, sum all of the output. So, your Z pulse, if you sum what is happening, oh, that is in some sense the total response, the energy that is going to be proportional to the gamma that was deposited in the crystal, right. So, your Z pulse is nothing but sum of all the, so this is an important concept because it's this will be, we will have to analyze, we will have to do our image formation, we will have to explain what, unless you understand the Z part of it, it will be very tricky. So, this is nothing but for scintillation, one scintillation scintillates, right, your gamma, one gamma photon scintillates, gives out electrical signal in several photomultiplier tube. The maximum will be probably the line of sight where it is, but the others will also contribute. So, your Z is nothing but sum of all the outputs of the different photomultiplier tube. So, now the question is, how do I place it, where do I place it, right, where do I place it, where is this activity. So, I have, this is the net response in the detector, but where should I place, where is this activity coming from, because our goal is to say where the activity came from. Oh, the easiest way is whichever photomultiplier tube had the maximum, maybe that is the line of sight. So, you can keep it there, but the downside of that is your spatial resolution is only in the order of your photomultiplier tube dimension, right. So, better way would be to calculate where it is using some logic which we call it XY logic, okay. But the Z, before we go to the XY logic and say where it is, one more understanding of what this Z is. So, if you do this for every scintillation, right, for every scintillation you get a Z, that is the, right. So, if you collect this during data collection, you collect it and then you plot it, right. What happens? You have pulse height. Pulse height is what? Oh, pulse height is is correlated to pulse height is what? Z pulse height is, so it's correlated to the energy that came in, because it's a total, right. So, pulse height and number of pulses that came, if you plot this, you will see this kind of a easy on eyes to look, but it has some strong markers to look at. What this says is, what are we sending? Gamma with one energy. So, ideally what should happen? Only that energy should come, right, but that is not the case. this pulse height is related to the, right, because pulse height is nothing but sum of, so it has to be, right, you are adding everything. Okay. So what you notice, when you add, you also get energies that are low, right. When do you get energies that are low? Oh, when you have not the actual photon that is released, gamma photon, because that is engineered, right, your radio tracer. But this gamma tracer, when it interacts with the crystal, there could be Compton scattering, right. Or when this gamma which is interacting in the body, the radio tracer has to come out of the body, right, the radio gamma has to come through the tissue. Maybe there at some energy level, maybe there is some scattering happening as well, Compton scattering, right. So there is Compton scattering that could possibly happen when it is trying to exit the body, depending on the energy conditions, and probably the interaction that is taking place in the scintillating crystal. That could also, because you get collimator and then this crystal, the crystal can not all of them give light energy. Maybe there is some energy that is interacting, you get Compton interaction, not just photoelectric. Compton scattered will go to a different location and there maybe it is generating the light photons. So what you, so basically the Z pulse, right, pulse height is related to the energy. You see that you will have a strong plateau. So no matter what, you are having Compton scattering, which thankfully here the Compton scattering is there throughout, but we can kind of know it from the plateau, right. So what happens here? Oh, when you have interaction, we talked about Compton scattering. When is the lowest Compton scattering signal, right? We talked about Compton scattering, h mu comes, h mu dash goes at a theta angle. When is the lowest energy? When the scattering is 180 degree. So this represents, Compton edge represents some of the, right, back scattered. So there are also those, okay. So what is of interest to us? Our interest is to define what is our signal. Our signal is photoelectric effect, where the energy of the photon is in the direction or from the photoelectric effect, where this conversion of this gamma is proportional to your light. So where there is peak, that is the guy, but usually you have a tolerance, right. So within a range of, or within this gate, so you get and you say this is my signal. Remember we did similar thing, h mu dash, h mu, what is the angle along, until when the Compton scattering signal will also be considered as a signal. We did that in X-ray as well, right. Similar thing. So whether you want to allow for Compton scattering until 30 degree, 50 degree, because your signal is going, we cannot clearly stick with only one signal, you need more photons. So your signal to noise ratio, remember. So the idea is you can have, this analysis is important. You get one scintillation produces an output. That output we call as Z pulse, right, sum of all photo multiplier tube. Then we analyze this in relation to a threshold and say, okay, if Z, right, if Z value is beyond less than this, for example, you don't bother about it. You think that is not your signal, that is only Compton scattered signal. You don't want to waste your effort now to say where that signal came from, because you cannot say it, you know it's Compton scattered signal. So you will be wrong to put that in the line of sight. So you kind of collect all the signal, do this Z analysis, right, what we call as pulse height analysis, and then we figure out what is the signal, right, which scintillation is produced because of the signal, that is the gamma, not the Compton scattered one, and which is not, okay. So it can be used to remove Compton scattered. So this analysis of height is used to remove the scattered photon, and also what are, okay, Compton scattering, we know energy is less, so less side is fine. What is this greater side? Oh, you could have sometimes you have multiple events simultaneously recorded, multiple events that are coming from different directions, multiple interactions. Sometimes if that happens, you get more signal, but then there is no meaning in saying which interaction you are talking about, because you cannot tease that out. So you have a region where you think based on the energy, you can set the tolerance, you can say that this scintillation is related to the radioactivity, meaning I can use this scintillation information to locate where it came from, and therefore in the crystal, and then therefore where it came from the object. Okay. So discriminator circuit. So you have a circuit, so Z pulse height analyzer, you have a circuit which will do this and detect the peak or within the threshold. Anything beyond that, that scintillation event will be discarded, will not be used further. How can it be used further? What is the next step? Next step is, okay, if I believe the scintillation is not corrupted by Compton scattering, so it's not some scattered signal for which I cannot tell from where the origin is, then if Z analysis tells us that, so if you collect your Z, only those events that falls within the whose Z pulse falls within the threshold is a valid event. If that is the case, then what we need to do, we need to then talk about where it came from. Okay, now this scintillation is valid, where did it come from? Activity and location. Where is the location? So we have what is called as positioning logic. Like I said, the easiest position is the photomultiplier tube that contributed the most, right? Could be the easiest guess. So that's probably the closest one to the where this gamma rays came and scintillation happened. It is right, but then that is only give you a resolution in the order of your multiplier tube dimension. Rather, we could go for center of mass, right? So if you denote x and xk, yk as your location for your center of your photomultiplier tube, we can use a center of mass instead of just using the photomultiplier tube with the maximum response as the location. Instead of that, we could use center of mass. How do we do that? So you have your x location to be xk ak. So this 1 z is what we calculated, right, total. So 1 by z of partial contribution. So this is waiting for location and the amplitude in x direction, location, amplitude in y direction. So equivalent to your center of mass calculation, right. So you can get your x and y. So now we have our activity, right, and where that possibly came from in x and y location. Clear? So that's all, right, we got it. Now the question is, what are the different acquisition modes? So when I do this, the radioactivity is coming, you cannot stop the sources. After you prepared the patient, the radio tracer is giving out, no control over that. So in the detection, whatever we saw, what are the different ways we can operate it, or what are the different acquisition modes that are possible, right, that will be meaningful, that can be used to our advantage. So essentially you have different modes, starting with the list mode to a whole body mode. We will go one mode at a time, right. These are very intuitive, because you know the important aspects, the Z analyzer, x and y location. If you know that and you understand how this is coming, what is this signal in relation to what is the source that is sending out, right, then all of this are pretty straightforward way of exploiting this information for a particular application. First is your list mode. What is a list mode? I am not giving any image or anything. This is just listing, right. So you collect this data and report the data in this form of list. So I will have x1 comma, so each scintillation event, right, I have n scintillation, so many photons came out. So x1 y1, in that scintillation event, amount of energy, right, what time it occurred. So I just have a list view of this. The advantage of this is kind of raw data that is well organized. Okay. Of course, it will have events that have passed the Z-pulse analyzer, right. It has to go through only those events that you think are going to be contributing towards your, because your x and y you anyway calculated only for those events. So this is your list mode. It has complete information, but no matrix or images. This is just list, you print out, you look at it. Okay. I mean, this is useful because it's kind of a raw data. Right? You have this information, they stored it, but if you have this, what is it that you want to do? You may want to visualize this, right? So the easiest visualization is your single frame mode. So this is your, right, mesh grid, right, of your imaging grid, if you want to call it, and this we know, this is your detector, and then all these little circles are your photomultiplier tube. So based on the analysis, you know x comma y, what was the z, right. So what can I do? The value in each pixel indicates the number of events happened. So if I keep the grid, I have one scintillation, I have one x comma y comma z. Next scintillation happens, I add it. Next scintillation happens, I add it. So I keep on adding. So I have one frame, the each pixel, right, x comma y comma z. You add, if each scintillation, you map it to the same grid and keep on adding. What will happen? Over time, because the radioactivity is happening, right, radioactive decay is happening over time. So if you do this, what is going to happen? It is going to catch. So after some delta t, you have a static frame where you can probably see which activity, which location had collected maximum activity, right. So in this way you have the entire, so this is called a single frame mode because you just have one frame for the entire scan time. So the patient has been scanned for 10 minutes, for example. At the end of it, you have only one output, right. So the advantage of this is, I mean, as the signal decays, more signal is coming, right, your signal to noise ratio will be high, right. So you can keep on accumulating the data. Of course, the downside is if there is any motion or anything, right, because radio tracer is there, the motion, then there will be some blurring, but otherwise this is a mode where you could get single frame, you can get all the signals added. So your signal to noise ratio could be high. So typical matrix size of 64 cross 64 or 256 cross 256 at the higher end will be used. Okay. This is single frame, but then you see already the limitations, you have added everything, right. What if there is motion in between? What if I want to see the rate at which something, so I send the, I want to see each time blood is circulating, it goes into some activity and heart is pumping. So what if I want to see the rate of wash in or wash out of a contrast agent into a particular organ, right. So all those things if I want to do, I want to go for a dynamic frame mode. What is this dynamic frame mode? Very similar to your previous one. Previous one you added everything, here you don't add, you retain each of the frame with a time index. So activity, so small delta t, I have one static frame, right, one single frame I got, and then next delta t, after some time I have another frame. Next, so if I have n delta t, right, then that is my n frames that I have. Okay. So the idea here is if you want to do some physiological process that are transient, so I want, like I said, how something is washing in, right? I may want to use this mode. Of course, you can synchronize this and use as well, right? You can restart. So I can synchronize this some with external trigger, I mean for some other trigger, for example cardiovascular, which we will again see in the next slide. But then I can get ECG, right? So I know with high precision which part of ECG, which part of heart cycle I am calculating this or imaging this. So I can say, okay, I will trigger everything from the start of, so I will start my your detector for scintigraphy. You start it at the start of, say for example R wave, right? So I can time that. So from there on I can acquire this delta t over the full cycle, right? So this is one way of dynamic frame. What is another? So you talked about dynamic frame already. What is then multiple gated acquisition? So extend this concept. So for example, I am imaging heart. See, dynamics, if it is just how the radioactivity is coming from some anatomy, right, that is static, that is not moving, then okay, the first image itself is good enough, like single frame, right? After some time I know whether the activity is there or not. Whereas if I have dynamic like heart, if you want to image, we already saw the dynamic frame, but then what is this gated dynamic? Maybe the delta t that you are acquiring has only some signal to, because you are, see, the idea thing is, if I wait for long I can get more photon count, my signal to noise ratio can improve. But then I want to catch this which is moving. So I have some, inherently I have to have less delta t, right, so that because it is moving. So then how do I maximize this? How do I get good quality signal or signal to noise ratio, so that every phase of this pumping I can have good image? Oh, the good news is this is not stopping, right? It is continuously doing. So you have multiple cycles. So if I gate it correctly, then I can collect the data over multiple cycles and stack them correctly at their phase, whichever, right, all the R phase from the multiple pumping, I can stack them together and then use that as one value. So multiple gated data is right, you have in ECG you can use heart imaging, like you could use ECG as a trigger signal. You can align that based on that high resolution, you can temporal resolution, you can organize your frames, okay. So whole body scan, this is not that difficult to, essentially you have one frame, register it, move to the next, register it, move to the next. So you juxtapose so that you have for the whole body. Of course you can time this so that, the idea is the radioactivity you put in, you have engineered, so it is going to give radioactivity, okay. So if you want to keep the count, so you know when to start, maybe the acquisition time is going to be little more, because you have to locate, do this 2D frame at different locations in the body, right, till you cover the whole body, okay. So that's for your different modes of imaging. What we will wrap up is, after you acquire all this data, what is our imaging equation and what is our, because we have to contextualize this is all now the detector frame, right. Eventually we want it in the patient frame. So we will go into imaging equation, right, using one of these modes that we have talked about. If you acquire the data, we will go to the imaging equation. After that we will conclude with the quality of the images, okay. Thank you.